superhero paper idea this morning. So one of you has decided. That's great. Friendly reminder, your deadline for is Friday. And yes, you may just email me those if that's more convenient. All right. There was only one little thing I didn't get to on chapter 14, and it's not as mission critical, but I think you guys will appreciate it and need to know. So it was about Bernoulli's principle. The concept is more important to us, and I told you what that was last time. Does anybody remember? Feel confident you could define it? What's Bernoulli's principle? What's the gist? Something to do with pressure. Good. There you go. The faster a fluid is moving, there's a corresponding drop in pressure, and vice versa. If the pressure drops, the fluid goes faster. I don't think of one as the cause and one as the effect. They just kind of go hand in hand. That's Bernoulli's principle. Where your book, again, defined it as where the speed of a fluid increases, internal pressure in the fluid decreases. And I'll emphasize that. That means in the fluid. So like if it's in your bloodstream, if the blood starts moving faster in one spot, there'll be a corresponding drop in pressure in the fluid there. So it'll exert less pressure on its surroundings. But let's say the blood comes, unfortunately you get cut and it starts squirting out and hitting you in the face. Gross, right? That's hitting you with a force. And that force is over a different area. That'd be a different pressure. This is the pressure within the fluid, not a pressure it would exert on something when it runs into it. That's different. So another example, I did it over here. There was that cylinder of water and it had 3 holes. Do you remember that? Which one shot out the fastest? The bottom, right. It was under greater pressure there because it was the deepest. And so it shot out faster. Well, in that water stream, it was moving. So within that stream shooting out, there was less pressure in the stream itself. Now, if that stream were to run into something and hit something, that's a different pressure. Because that's a force over an area, Pascal's principle, pressure. So we have the pressure from static things, and when forces are exerted over areas. But Bernoulli's principle deals when fluids, any fluid, is moving. You also have an additional or separate drop in pressure.
I was thinking about this over the weekend.
Good.
Like when the floods and stuff apply a lot of pressure when they go against buildings and stuff. So could you kind of elaborate more on the pressure that's in the fluid? Because what comes to mind when we say that is always the pressure that's being applied by the force.
Yeah, that's one reason I brought this up. Go over the pressure in the fluid. Because, you think of a dam breaking, and all that water comes and smacks in and can knock a whole house down. Well, that is, all of that liquid exerts a force on the house. The area of the house. That is a pressure. So it's exerting pressure on the house, force over area, and it can knock it over. Bernoulli's principle deals with the pressure in the fluid itself. And something we didn't discuss, your book explains it better than I do, I think, on this one, but they call them streamlines. This might help some of you with this. If you had a tube that had a big area over here and a small area here, we did an example over here. You can think of the fluid. Some of it goes, right on through. One here is coming along, but it kind of gets mushed together. And maybe this one gets smushed together. One over here, it gets deflected and it's another one. I think you get the idea. They're all moving that way. So to keep the flow rate the same, we had the continuity equation. So the speed here compares to the speed there. You're getting smaller, so it speeds up to get the same amount through. Thus, there's a corresponding drop in pressure here. And if you just pick this streamline, let's say, you just look at this guy. That's what aerodynamicists do. They just kind of pick one streamline when they're thinking of this often. And they go here and, oh, it was constricted. It's deflected. And so it speeds up. And so the pressure, the fluid right here exerts on its neighbors. So on this streamline, and say on the inner wall there, that decreases. If this now opened up and shot out against a wall, that would be this. It's a different pressure. The pressure within the fluid that it exerts on its neighbors. And in this case, yeah, because it's a smaller area. If we went the other way, and the fluid was flowing like this, it can expand. It's not constricted. You can see the streamlines spread apart. So it'll actually slow down and exert more pressure on its surroundings. So this one would exert more pressure on his neighbors. That's what we mean within the fluid.
Like looking at that picture, wouldn't the compression of that cause more pressure to build?
No. Because it's in motion. Yeah, I think you might be thinking, yeah, if you keep trying to shove more and more of a fluid into a constrained space, yeah, it's going to compress, and that would increase pressure. But if it's free to flow, so I wanted to emphasize Bernoulli's principle. Since we had a whole chapter on energy, Bernoulli's principle really is just a way of saying conservation of energy for fluids. And that's the part I didn't get to. I'm doing one of these math things again, but just to show you. So we've looked at these forms of energy: kinetic energy, gravitational potential energy, and work. How it transforms from one to another. Total energy is conserved, so the sum of all this should stay constant. This works for fluids also. This is Bernoulli's equation. They don't write it this way, but this is what it means. So I'm starting with this. We know kinetic is 1/2 mv squared. It's still a mass of fluid moving at a velocity. It can change positions. It can go up to a water tower. It can come down. It can move around just like we can lift objects up and down. So it can gain and lose gravitational potential energy. And work. It can do work on things. It can have work done on it. Just like other objects, when they hit things, they can do work on them. This one is a little funkier. So let's look at work. Work was force times distance. You guys are all going, oh yeah, right. Right? Good. From Pascal's principle, what's force? So we're dealing with fluids here. So we're going to represent force as pressure times area. I don't expect you to have to repeat this. So this is another way to look at work. It's a pressure times an area for a certain distance. And area times distance is volume. Remember, an area for spread over a certain distance, it gives you the volume. So now we're in terms of fluids. Pressure times volume is the same thing as work. That's still constant. So 1/2 mv squared, mgh, pressure times the volume. That has to all stay the same. And all they really do, little trick, they divide everything by volume. Divide that, whatever constant that is, by volume. You can do that. That keeps everything equal. What's mass over volume? Density. 1/2 density velocity squared. Density. Does that look familiar? It's the pressure, right? And this is just that pressure. A new constant. But it's still a constant. That's Bernoulli's equation. It is in your book, but they don't use it as much. But what we can learn from this, a guide to our thinking, is total energy is always conserved, even for fluids. So if you were to do a ride like this, I don't know, let's say you started up here and then you went down and then came back up. If you were in a tube and you shoot water through there, do you see that this one's changing? You have more potential energy, less potential energy, more potential energy, but not as much as you started with. That'll change throughout. If this goes down, something has to give, doesn't it? If the gravitational potential energy goes down because you're lower, but we have to keep the total constant, what do you think changes? At least in this situation. Velocity could change. It could speed up. That was kind of like the cylinder here where it shot out the hole. This one, phew, it dropped gravitational potential energy. It was turned into kinetic energy. In this case, it's still confined. But you know that when you're deeper, down here, has this fluid on top of it, pushing on it. So the pressure is greater down here than it is up there. That's why they build water towers. Fill it full of water, store it up for us in case of an emergency, but they put them up. Because when you get it down here, into a hose or a pipe to take it where you need, the pressure is larger down here than it is up there. So you have enough pressure to push it out, increase its kinetic energy per volume. You've got enough pressure to do that. And you can get it to your homes. So the idea here is these still change just like we had before, no matter what the object. Does that make sense? I like when it's consistent. Thought I would show you that. Alrighty. We finished 14. I prepared some clicker questions for you. Let's check some of our understanding here. There we are. Now we can see things. All right. Let's go over this a little more then. We'll review. So we've discussed how things change when we get up there. Polling's open. People are responding. It's registering. Sorry, it's first one. I take longer on the first ones. Are you? I'm on channel 41. Is yours still on channel 41? No problem. Yeah, you're on the wrong channel. That's why. So we hit channel 41. Okay. Check. That's good. All right. Vote away. Let's see. Huzzah. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Get my cursor. There we go. Large majority of you both. Good. Both of those things change. There's less air up there, so it's less dense. And you're higher up. You have less air on top of you, so the pressure is less as well. It's the weight of that air on top of you, acting over that area, force over area. That's pressure. Questions? Okay. So 2 tubes, one's full of air, one's got some water in it. If they're going to have the same pressure at the bottom, how much water needs to be in that one? Thought another way, you got so much air, it weighs something. You got so much water, it weighs something. You can strain them to a tube. When are they the same weight? How much water weighs the same as all that air? Yeah, they're giving you a clue that the tube with water is not all the way full. It's one of these answers. Full. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Most of you A, 10.3 meters, that's correct. Water is more dense than air, so it's heavier. You don't need as much of it to weigh the same as all the air. And we've used this example many times, and so does the book, that if you have 10.3 meters of water, the pressure at the bottom is equal to 1 atmosphere of pressure. It's equivalent to what we're feeling right now due to the atmosphere. Questions? Yep.
But if you have, say, the 2 tubes, one's completely air, and then you have one that's pressure filled with water, wouldn't the air on top of it add to its weight?
Yes. Excellent point. The one full of water, the pressure at the bottom technically would be 2 atmospheres. So when I was giving you a clue, I probably shouldn't have said pressure the same at the bottom. So I'll give everybody credit to this one. I think the question words it better than I did. Yeah, the weight of the fluid in each will be the same when the level of water is 10.3. That's still true. Because the weight of 10.3 meters of water is the same as the weight of all that air. But you're absolutely right. The pressure at the bottom of both of those, it'd be twice as much for the water because you'd have all that air and water. Excellent point.
This may be a little off subject, but like if you can't, there's some people who can't go deeper than 4 or 5 feet in water because the pressure on your ears.
Uh-huh.
How come 10.3 is the same as the pressure we're feeling right now, but some people can't go that deep without their eardrums?
Another good question. And it's related to his point. Think about it a moment. When you're down 10.3 meters, what's the pressure on you? Yeah, because you still have the air above you in real life. So we can handle one atmosphere just fine right now.
Okay.
But yeah, add another one on top of that, owie.
Okay.
And that's why our ears hurt when we go up in an airplane or underwater, because we're going away from one atmosphere of pressure. Good. I'm one of those that I don't do well with that. All right. I like this question. We'll see if you like it or not. It's hit or miss. Some students like it, some hate it. Big steel tank. Let's put some helium in it. What's different? This requires a bit of thinking. In other words, most people's knee-jerk reaction isn't right. That's your clue. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Bang. All right, we like B and D. Most of you like B, but some of you don't like any of them. So the majority didn't get this one. Those of you that answered D, will you help me explain? What was your thought? Yeah.
I was thinking, like, if you have balloons in your car, it's still the same.
If you have balloons in your car, what's still the same?
Nothing's changing in your car. The weight's not changing or anything.
Its weight doesn't change. What if you were to pump more helium into the balloon?
Well, the balloon would fall.
Well, what's the difference between a flat balloon and pumping enough helium into it? What happens then? It expands, explodes. Before it explodes, what might happen? Its volume increases, thus its density changed of the whole balloon, not the helium, but the whole balloon. Thus, ooh, now you're thinking like physicists. If the volume is increased and its density is decreased, it can float. The buoyant force changes, and it goes up. What's different in this case? It's not a helium balloon, it's a steel tank. The volume doesn't change. So the buoyant force on this does not change, because we're not changing the volume of the tank. If anything, you're pumping more helium inside, that weighs something. Not much, but it's something. If you keep pumping it in, it's actually the whole thing's going to get heavier. The whole tank is becoming more dense because you're shoving even more helium inside of it. To help? Yeah. That's why we're in a class. It's okay.
When you pump it full of helium, it expands and displaces more.
If you pump a balloon full of helium, it's free to expand. Yeah.
And so when you expand a balloon with oxygen, why doesn't it float as much?
If you expand a balloon with oxygen, there we go. Okay.
The volume's the same, but what about helium?
So it still expands. That increases the volume of the air it displaces. That should increase the buoyant force. You'd think it'd go up. But as somebody else mentioned with the helium, what else happens when you pump oxygen into the balloon? We're not just changing the volume, we're also changing the density. Oxygen is more dense than helium. And so there's a balance there. Okay, we're expanding the volume to increase the buoyant force, but we're adding more oxygen, which can make it heavier. And so if it could be big enough with oxygen in there, it could float. But the oxygen could be weighing it down because it's too dense for what it's making and expanding. Does that help?
Yeah.
And I have never seen
You've never seen a helium tank floating. Well, that's the idea. You know, you got your helium tanks to blow up your party balloons.
No, in the car.
Well, I know, but there's a tank, a steel tank, right? They fill it full of helium, shove more in, compress it. That increases the pressure inside the tank because it's fixed. That was your question. But yeah, it doesn't start floating up. Well, you think, well, we'll get enough in there. You know, because if it was free to expand, then maybe. But that tank isn't. Were you teetering on something? Yeah.
No.
Okay. So I like that question. It's a thinking person's question. All right. Now we do have a hot air balloon. We're not a steel tank. This is our last one. I like giving clues. I don't mind. If it's hovering, what's another term we've used? We could say the thing is what? Oh, good. Neutrally buoyant. That's a clue. Neutrally buoyant. Say that again?
Hummingbirds can be also neutrally buoyant.
Yes, hummingbirds can be neutrally buoyant. Fish can be neutrally buoyant. Submarines can be neutrally buoyant. They can all hover if they choose to. So in this case, if that's true, what's the weight of the balloon? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 84% B equal to the weight of the displaced air. Excellent job. If it's not going up and it's not going down, then the forces are balanced. The weight down is balanced by the buoyant force up. If the buoyant force were bigger, it would be going up. If the weight were bigger, it would be going down. Neutrally buoyant is hovering, they're equal. The net force is 0. It's not accelerating, it doesn't move. Oh, sure. Tell me when. You can put your clickers away. That was the last one. Yes?
So would it be safe, back to the first drawing that you would it be safe to say that water in motion is lighter than water?
Is it safe to say water in motion is lighter? No. No. It's an excellent question. I want to say no, because it's within the fluid. You still have the same amount of fluid at any given time on your scale, so it still weighs the same, but the pressure inside can be less. Because it's exerting less pressure up, but it's also exerting less pressure down. Maybe all of that balances. I have to think about that one more. Water in motion, does it weigh less?
Fluids are, for the most part, incompressible.
Most fluids are incompressible.
That's why we get
Yeah, or it's water was considered incompressible, which again was why you don't want to fall in water. It's still going to hurt. Air is compressible though. Because there's space in between air molecules. All right. Couple fun demos on this moving stuff. Need a volunteer. Who? Never mind, I'm not going to say that. All right. I'm going to ask you to blow up this bag. We're going to count how many breaths it takes. Exactly. 1, 2, 3, 4. Oh, that's enough. I'll spare you. All right, there we go. You filled it. You can let go, but you're not done.
Okay.
You hold that in. Knowledge is power. I know Bernoulli's principle. And if I can get air moving fast enough, there'll be less pressure in the airstream. And if there's less pressure in the airstream, maybe we can draw some fluid in with us. Because less pressure in the airstream, more pressure out here. There's also some viscosity. So most people, without me saying anything, put their mouth right up to it. I'm going to have my mouth farther away and just go, one breath. But this isn't all from my lungs. It pulled in air with it. So that's kind of fun. Thanks. This is called entrainment. If you want to learn more about entrainment. E-N, train, choo-choo, woo-woo. I can write it on the board. Prairie dogs and groundhogs will use this to cool their tunnels. Entrainment. So example, you got a mound up here and maybe another hole here. So they got, tunnels. Well, hey, if there's a breeze up here, then the fluid's moving across the top, right? It gets deflected or constricted. So what happens? It's moving faster here than here. Difference in pressure causes air to flow. Less pressure, greater pressure. Remember me pulling things up the other day? Faster moving fluids have a corresponding drop in pressure. And that can draw air up through here. It'll actually draw it in here and get an airflow going through there. One way to keep them cool. Another way to show that is with a ping pong ball. Oh, do this one. It's not an exciting demo, but I recently got this. They have bigger ones, a Dyson fan. Maybe you've heard. They got a little opening on the inside. There's no blades, so you turn it on. There's no blades, so you can't hurt yourself. What it does is it does pump air, but it blows it out in here. It's like me blowing in the bag. And as it blows a little air, it gets that air moving, and it draws in other air. So this can move a greater volume of air than a fan the same size with just some blades spinning. And, it's safe for your little kid, right? And it's got cool lights. But it uses that entrainment principle, Bernoulli's principle. You have to practice on this one, but go home and try it out. You can take a ping pong ball and trap it in your airstream. So if you can get air moving quickly enough, there's a correspondingly drop in pressure enough that it stays trapped in the airstream. It's deflected around the edges. It's constricted, so the air's faster on the edges. There's lower pressure right next to it. The greater pressure in the room keeps it in the airstream. So when it tries to go out of the airstream, nope, push you back in. When it goes this way, nope. Now, that's Bernoulli's principle pressure. What's holding it up is my air pressure. I'm just blowing into it. My air's just running into it and smacking it. That's a different pressure. So my air pressure's holding it up, but it's that difference in pressure from the air moving around the sides that keeps it in the stream. If I could go fast enough, I could hold this one up. But I can't. This is too heavy. But this can go faster. That's right, it's the air around the ball that keeps it in the airstream. This moves the air and pushes against it, but it's causing the air to deflect and constrict, and it's probably pulling some other air with it. And it's that drop in pressure on the sides. Even, when it's tilted. The air, this has weight down. There must be a corresponding lift pressure up, which means the pressure here must be less than here. When it tips, the air here gets deflected and constricted more. It moves even faster than the air down here. And that creates a corresponding difference in pressure. Lift. Same thing with an airplane wing. All right. What do you think will happen now? It'll blow the sieve off? Good observation. The air, the air's more constricted here than here. This is kind of just like going through the tube. We're changing the area. Here, it's smaller. Here it expands. And with continuity equation, the air then is moving faster here than it is here. So the pressure is greater here than it is here. Where it's moving faster, there's a corresponding drop in pressure. And it's that difference in pressure that actually keeps it in, even when it's upside down. Yeah. So this one, it's spreading it out, and you increase the pressure. If you blew this way, you could decrease the pressure. That was good. I'll go with that. Okay. I got nothing more on 14. We're supposed to start 15 today, so I'll start it. So this is a little transition. The topics might seem a little different. I'm going to try to make the connections. So we've been doing fluids, liquids and gases. Heat and temperature is chapter 15. And then 16 will be heat transfer, how we can move that energy around. In 15, though, I like to think of as heat as a fluid. Historically, they did. They called it the caloric fluid. A calorie. That's a unit of energy for heat. It's not really a fluid, but you can think of it because it flows. We're not dealing with individual objects anymore. We're dealing with a bunch of them, just like with fluids. And we measure temperatures, and we have heat and energy, internal energy. To begin with, let me show you this demonstration. So to kind of picture this microscopic stuff, good enough. All right, so I got a bunch of BBs in here. And think of that as a solid, or a gas, or a fluid. It doesn't matter. It's an object. But it's made up of particles that we usually don't see. And they're always moving. They have a temperature. And so they're wiggling around. They got energy. They're wiggling around. And they bounce all over each other. They're having collisions. They're transferring momentum. They're exerting impulse. They're changing their velocities. Sometimes they're moving fast. Sometimes they're moving slow. If you make it hotter, they move faster. Watch some of them. Sometimes they're in focus. You can tell they're moving more slowly. But sometimes they're really blurry. They're moving quicker. That's what's going on in everything. The air in the room, they're jiggling around. The air or the particles in this table are jiggling around. In water, they're jiggling around. The more they jiggle, the more they push on their surroundings. The less they jiggle, the less they push on their surroundings. They exert pressure. I bet you already knew this. If you contain something and you get it hotter and hotter, the pressure increases, right? If it can't escape, you'll make a bomb. That's bad. Well, that's why. you're giving more and more of these particles energy. If you put heat in, you add heat, energy, they start moving faster and faster, and they start pushing more and more. There's more collisions with the wall, and it'll expand if it can. And if it can't, the pressure will build up until it breaks, and you have a bomb. Questions about that? This is our visual through these units. Any particles. So like if you're thinking of this table, it could be the atoms and molecules in there. If you're thinking of water, it'd be H2O. The air in the room, nitrogen, oxygen. Okay. So let's define a few terms so we're talking the same language. Yeah, that's probably where we'll get. This is chapter 15. All right. Temperature. And these are defined in your book. That is a measure of average translational kinetic energy per molecule of a substance. Again, it's a particle, depending on what you're talking about, per particle. All right, let's break that down, because this is important to help you with a lot of these questions and concepts. Generically, temperature is a measure of how fast the things are moving. If they're moving faster, they're hotter. And if they're colder, they're moving slower. But more specifically, it's the average translational kinetic energy. So like those BBs, sometimes they're moving fast, sometimes they're moving slow, but on average, they're going a certain speed. And if they have a certain speed, on average, the kinetic energy, average squared, they have a certain kinetic energy, on average. But realize that means sometimes they can go faster, sometimes they go slower, and they change. So it's average kinetic energy. Another thing that's important is this word translational. We haven't used much. It means in a straight line, because molecules can do different things. Here's like a complicated molecule. Here's maybe like a simpler molecule. Think of this as a water molecule if you want. It's not really, but you know. You got two atoms. Translational means the whole thing's moving. That's how we've dealt with objects so far. They're moving around as a unit. If we're looking at this molecule, then we mean the whole molecule moving around. That's translational. So the average translational kinetic energy per molecule, the whole thing. So for this thing, it'd be the whole thing moving around. But molecules can also move differently. This one can rotate. It can rotate this way. It can vibrate. It can flex. This one can wiggle even more. They can all be going, but the whole thing isn't translating. So it can have different energy. It can have more energy than just kinetic energy, translational kinetic. That's called internal energy. That includes everything. That's everything. So, a molecule can have internal energy. That counts for everything. But temperature is only a measure of the average translational kinetic energy. It doesn't account for all of that motion, just the translational. You with me? Don't worry, we'll apply this as we go along. You're like, yeah, I get it, so what? But these are two different terms. Temperature is conveniently, noted with a nice big T. Internal energy is most often referred to with a big capital U. And heat is another one. It's usually a big Q. Heat. What is that? That's the energy that flows. See, they still use that term flow, like a fluid. Is transferred, in other words, from one object to another. But it doesn't do it spontaneously. It does it only by virtue of a difference in temperature. And I'll get out of your way so you can see all this. So heat is the transfer of energy. But it only is transferred if there's a difference in temperature. We've seen this before. Things will go downhill only when there's a difference in gravitational potential energy. Fluids only move when there's a difference in pressure. Heat only flows when there's a difference in temperature. And it always flows from hot to cold. Never the other way around on its own. It'll never spontaneously go from cold to hot. It always goes from something hotter, a higher temperature, to something at a lower temperature. Now you remember when we discussed work, and I tried to emphasize that objects, we don't say this has work. It has energy, and it has the potential to do work on something else, or I can do work on it. See, I raise it up, but then I drop it, and it does work on my hand. Work is kind of that transfer of energy. Heat's like that. Heat is energy in transfer. But it's only transferred if there's a difference in temperature. So it's temperature that dictates whether heat flows, not internal energy. Idea about that. If we had a big pot of water that's warm, and a little cup, whoops, that's hot, of water. They're both water, let's say. Which one has the greater temperature? The hot. That means the little water molecules in here, on average, are moving faster than the ones in here. Which one has more internal energy? The warm one, but they're moving slower. But there's more of them. Bingo. So it would depend on how hot and how big, but yeah. So yeah, per molecule, these have more energy, kinetic energy, because they're hotter. That's what temperature is. So these have less average translational kinetic energy, but man, there's a whole lot more of them. And so overall, that can add up to more energy. So this would have more internal energy. There's more of it than this, but this is hotter than that. So if we poured them together and mixed them, let's say this was 100 degrees Celsius and this was 50 degrees Celsius. When we mixed them, what do you think the final temperature would be? Less, more, or equal? Did you think the final temperature, if you mix these, you poured that in there and measured the new temperature, would it be 75 degrees? Greater than 75 or less than 75? Less, because there's more of this. This has more internal energy, so the final temperature would rest here. But temperature will flow from the hot to the cold. This is hotter, so it's going to flow from this. This will decrease temperature. This will increase temperature. So it's temperature that decides heat flow, not temperature. So there's our definitions. We can do a lot with that next time now. Did I say that incorrect? This has more internal energy. the temperature will flow from the hot to the less hot. So this will get colder, this will get warmer.
So it's length that determines.
So it's temperature that determines heat flow, whether it flows and in which direction, not internal energy. Good catch. Thanks.